Hello, I'm Edward Tarte, a math teacher. This is another in a series of solution videos to some of my math challenges. The math challenge for this solution video is my geometry areas challenge. In that challenge, I showed this figure, an equilateral triangle. It means a triangle with all three sides equal, and within it, touching it at 3 points, a circle. Within that circle, touching it at 4 points, a square, and within that square, touching it at 4 points, an inner circle. And the question is, if a point is chosen at random from the area of this triangle, what is the probability that that point is within the area of the inner circle? That's a probability question. Probability questions, as I explained in the video, are answered by a fraction, a part over total fraction. In this case, the numerator, the top number of the fraction, will be the part, that is, the area of the inner circle, and the denominator, the bottom number of the fraction, will be the total, the area of the entire triangle. Well, here's my solution. The solution to this challenge depends on the two special right triangles of high school geometry. One of them is known as a 45-45 right triangle because each angle, aside from the right angle, is 45 degrees. It's also known as an isosceles right triangle. That means both legs are the same length. The simplest example of that is each leg has length 1, and by the Pythagorean equation a squared plus b squared equals c squared, the hypotenuse has length the square root of 2. Generalizing, each leg length a, hypotenuse length a times the square root of 2. The other special right triangle from geometry is known as a 30-60 right triangle. It is half of an equilateral triangle, that is, half a triangle with all three sides equal. You can see the other half that I've drawn here in red. The simplest example of that is the shorter leg has length 1, and because that's half of the length of a side of the equilateral triangle, the hypotenuse, which is also one of the sides of the equilateral triangle, has side length 2, and you use the Pythagorean equation to get the length of the longer leg. It works out to be the square root of 3. 1, 2, root 3. In general, short leg length a, hypotenuse length 2a, length of the longer leg a times the square root of 3. So that's a little background to lead into my solution to this geometry areas challenge. There are a bunch of ways to work this. The simplest way I know is to designate the radius of the inner circle as length 1. Now that inner circle, having radius designated as 1 unit, has an area found by the formula for the area of a circle. Area equals pi times the radius squared. In this case, pi times 1 squared. 1 squared is 1. That's pi times 1, which is simply pi. So the area of the inner circle is simply pi. And that is the numerator of our probability answer. So our probability answer will be pi over some denominator yet to be determined. That radius 1 shown here is one side of a 45-45 or isosceles right triangle. This is 1 also. It is actually half the length of one side of the square. And by that 45-45 right triangle set of relationships, the hypotenuse length is the square root of 2. That length, the square root of 2, as I've shown here, drawn to this corner, is a radius of the larger circle. I have redrawn that radius of the larger circle from the center straight down to the bottom. That length is the square root of 2. I have now formed a triangle. It's a right triangle. The right angle is here with that square root of 2, and I connected the center to this corner of the triangle, and we have this triangle from here to here to here. And we are now going to focus on finding the area of that triangle. Here is that triangle. I've shown it in red, and I have omitted the other figures so that they will not distract us. Again, this length is the square root of 2. This is a 30-60 right triangle, the triangle shown here, because this angle of the large equilateral triangle is 60 degrees. This splits it in half. That's 30 degrees. This is a right angle. This is 60 degrees. And therefore, because of the 30-60 right triangle relationships, this longer leg from here to here is the shorter leg times the square root of 3. That's the square root of 2 times the square root of 3, which is the square root of 6. We can use the square root of 2 and the square root of 6 as the height and the base of this triangle and find its area. The area of a triangle is 1/2 the base times the height. That will be 1/2 the square root of 2 times the square root of 6, which is 1/2 times the square root of 12. 1/2 times the square root of 12, I split the square root of 12 this way, 1/2 times the square root of 4 times the square root of 3. The square root of 4 is 2, so 1/2 times 2 times the square root of 3. 1/2 times 2 is 1. So that's just the square root of 3. So the area of this triangle is the square root of 3. How can we use that fact, this area is the square root of 3, to find the area of the entire equilateral triangle? Well, there are 6 triangles all the same size, like this one triangle, to comprise the entire triangle. So we simply multiply this area, root 3, by 6 to get the area of the entire triangle. That means the area of the entire triangle is 6 times the square root of 3. That will be the denominator of our probability fraction, 6 root 3. We said earlier that the numerator of our probability answer is the area of that inner circle, which is pi. And so we have our probability fraction answer. If a point is selected from within the equilateral triangle, selected at random, the probability that that point is in the area of the inner circle is pi over 6 times the square root of 3. So that is my solution to my geometry areas challenge. Thank you for watching this solution video.